So I'm going to do my best to capture the essence of the conversation. So our group was tasked, as Joe pointed out, to discuss the opportunities in pre-CAD conceptual design. So how can we use simulation to affect the pre-CAD conceptual design as a way of expanding our market and impact? So this slide captures at a very high level the essence of what we were thinking about. And this really carried on from the premise, the revolution that Joe spoke about and that Richard Riff introduced. So if you look back 10 years ago, there was an estimate that maybe 1 in every 20 or 22 engineers were using simulation. So over the last 10 years, we've actually improved that number to 1 in 6. So the question is, what would it take to get to more or less all engineers using it over the next 10 years? So that was the challenge. And so the conclusion there is that we need to get pervasive use of simulation, because if you look at the development process, if you want all engineers, you have to impact the entire process. So this is kind of the theoretical development process. It's a little hard to see, I apologize. CAE shows up fairly late in the cycle. But over time, we've been able to move to that from out of 22, 1 to 6 by kind of replacing a lot of the virtual prototyping, a lot of the physical prototyping with virtual prototyping, and that's driving a lot more use of simulation. So we're getting some development use of simulation throughout the process. And the question is, can we get into the concept part? How do you do that? How do you do simulation when you don't actually even have geometry yet? That's a particularly interesting challenge. But if we want to get pervasive and we want to have maximum impact and get to all engineers, we have to get to that conceptual pre-CAD phase. So we concluded that the best way to do that, first of all, is to capture the knowledge of what we call the boomer wave of analytical science users. So there's a group represented very well by the people here who know this, who live and breathe it. We created this technology. But there's a new generation that didn't create it, that are just using it. They exploit it. That's the way technology works. So there's a great amount of knowledge about how the systems work that have to be built into the tools. So we have to build tools that as they go through this cycle, they're learning from us. And so we have much smarter tools. And we identified some analysis and topology optimization in particular as ways of addressing pre-CAD activities. So we hypothesized that a more non-traditional development process would look something like this, where not only do we affect the design phase, but we can get to the pre-CAD phase by exploring by using simulation to drive the technical requirements. Simulation can be used to take customer requirements and create the idealized product, which can then be used to drive the real product. And then you get a requirements-based focus rather than a geometry-based focus. And you can use simulation to test out the customer needs, to test out their ideas, what's possible, before you even get to commit to geometry, because once you've got that first CAD design, you're kind of locked in a little bit. So that really is the question, is how do you do simulation still when you don't have geometry? So topology optimization emerged as one of the more obvious ways of doing it, where you map out not so much a design, but a design space. So you start out with a rough idea of what you want, and you let the computer have at it based on its understanding of what will produce the best product. And here's a rough example. So you start with a design space that knows where the attachment points are, and it knows what the requirements are in terms of stress, performance, and then the computer does the rest. And now you get pretty close, and then the designer can do his thing to make sure it's a little bit better, because the computer can only go so far. So we now have a system that really does produce a form that follows function, because the computer is basically changing the form dynamically based on simulation in a way that a human would take far too long in process. So that's a technology we think is an enabling piece that's going to take us a certain distance away. But we still have a problem of conceptualizing function in many applications. So I put together this little diagram to talk about why, to try to capture one of the pieces that we talked around but couldn't quite articulate, where topology optimization wouldn't really help us. So if you take the simple example of trying to optimize the performance of this hunting tool, bow and arrow, you conceptually say, okay, I know how to use this. I have certain requirements. It has to fly straight. The arrow has to fly straight. I want to get the maximum speed, penetrate the target. And so I put that all into my system, and I generate some nicely engineered high-performance bow and arrow that any engineer would be proud of, with pulleys and all kinds of motors and whatever you need. And that's kind of recipe-based. It takes the bow and it says, okay, how do I make the arrow go faster? I put more tension on the cord and whatnot. But another way to look at it is to take those requirements and not be stuck and have a requirements-based optimization, and therefore you end up with a revolutionary design, something that isn't stuck with the original, but reinterprets the requirements in a new and innovative way. And that's something that today's tools won't do, but that's where you're going to have your most impact, because that's where simulation can tell you, you know what, I know you've been doing it this way, there's a better way. And that's what simulation can do for you. So we have to get to that level. So simulation can profoundly influence not just the ending part where you end up and finalizing, but driving where you start, because ultimately where you start is going to predict where you end. So we've mapped out some of the attributes that it would take for a successful simulation. We need products that are not heavyweight. They need to be easy to use. They don't need to have every bell and whistle, but they have to be performant and work like a natural extension of what someone would normally do. They need to allow you to explore direct space, sort of the analog of direct modeling, so you can get at it correctly. You need things like reduced order methods, subsystem modeling, this concept of spell check for designers. So if you make a change, the system says, hang on, that's not going to work. And then you go, okay, let me put it back. Or even better, you right-click and it tells you the right design. We'll get to that eventually. And this idea of good enough fidelity kept coming up. You don't always need the best simulation throughout the process. You want to be able to crank up the fidelity as you go through, and these guiding methods. So through that process, we talked a lot about disruptive technologies like 3D printing, and how that was going to challenge that idea of where you start, because people have optimized a lot of products like cars based on manufacturability, or what they've always known about manufacturability. And so I brought this example where, what you really might want is to be able to go, if you're doing conceptual, you want to sketch it, have something like this. This is what I want it to look like, and then kind of have the computer go off and design the car that best fits that concept. And this is actually a real car that's been designed. It's 3D printed car with a sheet over it, so there's no metal, and you could actually do it. But because you don't have the constraints of manufacturing, the computer just says, well, this is the best body, if you don't have to worry about putting the thing together. So throughout the process, there's a couple of running notes, what we called game changer ideas, topology optimization. Again, as I talked about coming up, but we need to understand the materials quite a bit, because as we get downward in scale and we think about 3D printing, we need to material properties become a real key element. Tools have to get smarter, so we need to not only have the physical dimensions, but we need to think about what's happening around them. As we think particularly in these ideas of working through 3D printing, we're talking about engineering the materials as we build. We're not taking pre-built materials, but we're actually building them as we go. So we need to have simulation has to affect the ability to understand that the materials are created dynamically, and we can change them, and their performance will be, the performance of the final product will be dictated by the actual manufacturing process. So we have to really think about that up front because that affects the downward part. And then we talked about some breakthrough technical approaches in the performance world that could definitely help bring CAD-less geometry or meshless simulation to the forefront. And that's it.
So we have time for one or two questions. Anyone? Jay.
Steve, question is about the possible inverse relationship between growing the numbers of users and pricing. And often in this industry, whether it's CAD or PLM, if you want to expand the market, increase the number of users, you typically see a lower ARPU over time. Simulation is typically, for the class of users you've had historically, relatively expensive. So if you could talk about, from the Simulia perspective or just from your industry perspective, how you think this might play out in terms of this pricing curve versus the expansion of the user base in the way that you talk about.
There's probably two schools of thought. One says that's just the way it is, and if you're producing tools that are not the dominant product that someone's using, you're going to have to lower the price versus because you're delivering less value. The other way to think about it is that if the CAD tools that they're using today become a helper to the actual simulation, so once the simulation says this is what you should design, and then the CAD tool is just the way of enabling it, we can shift the value of the seat from being dominated by a design tool and every now and then use the simulation over time to simulation being a design tool. And so the hope would be that we would be able to deliver the same value, but that's not going to happen in one go. So I think we're going to go through a trough, if you will, that people are going to have to get in and then grow value over time. But that's an opportunity because we're not lowering the revenue for the industry. We're adding it just as a thin layer, and then we penetrate and grow.
Eden?
Steve, could we think also about a possible hierarchy architecture of integrating the pre-CAD with the CAD tools? I mean, a hierarchical approach, considering different tiers, considering, let's say, the tier of pre-CAD as one tier of free thinking, and then to have the other tiers of going into detail of that free thinking.
Yeah, I think that the idea that the way that diagram was set up that I showed, the idea is that there's a conceptual stage and then you're done and you move into a design stage is probably oversimplified because that's the way it happens today because they're in different groups and different silos. So to really fix what I think we're talking about where simulation is pervasive, you want conceptual engineering throughout the process. You want to be able to innovate constantly. So you want a system that allows you to have the hierarchy, to be able to say, we've run into a problem with our design, let's go back and reconceive it, and then go back to design. So I think that's the way you'd want to implement it, but that's a rethinking of the workflow.
Okay, thank you. If you have additional questions, please write them down now and email them to me, and I will get them taken care of. One of the things that I want to point out is that these 7 presentations are presentations of what the issues are. They're not meant to be definitive about what the answers are. The whole point is, what do we need to be researching? Where do we need to be developing? Where do we need to be paying attention? And thank you for handling those, but there are no answers to any of this yet.